Hi again. This is Taylor and MacLourin series lecture. For start, we write a theorem. If f has a power series representation at A, then f of x equals fn at A by n factorial times x minus a to the n from 0 to infinity. We introduce a little bit of its proof, because f has power series representation, then at A, then f of x equals c0 plus c1 x minus a plus c2 times x minus a square plus dot dot dot. That is ci x minus a to the power of I from 0 to infinity. The zero derivative of f at A is f of A. That is c1 times x minus a is 0, c2 times x minus a square is 0, so c0. We can write 0 factorial times c0, so c0 is f0 at a over 0 factorial. F prime of x, the derivative of c0 is 0. The next one is c1 plus 2 times c2 times x minus a plus 3 times c3 times x minus a square plus by this f prime of a is c1. We can write 1 factorial times c1, so c1 is f prime of f at a over 1 factorial. The next derivative, the second derivative of f at x, c1, the derivative of c1 is 0, so 2 times c2, that is 2 factorial times c2. So sorry, that is f prime of f at a. 2 times c2 plus 3 times 2 times x minus c3 x minus a plus 4 times 3 times c4 times x minus a and so f prime of f at a is 2 times c2, that is 2 factorials times c2, because we can write 2 times 1 instead of 2, so c2 is f prime of f at a over 2 factorial. Then the next derivative is third derivative of f at x is 3 times 2 times c3 plus 4 times 3 times 2 times c4 x minus a plus dot dot dot. By this, f the third derivative of f at a is 3 times 2 times 1 times c3, 3 factorials times c3, so c3 is the third derivative of f at a over 3 factorial. So we can conclude that f power n, the nth derivative of f at a, is n factorial dot times cn, that is cn is f the power n, that is n factorial of f at a over n factorial. By substitute this ci in the notation of f at a by power series, we have f of x is c0 plus c1 x minus a plus c2 x times x minus a square plus c0 is c0 is the zero derivative at a over 0 factorial plus we can write times x minus a to the power of 0 plus the first derivative of f at a over 1 factorial times x minus a square plus dot dot dot. That is the last step, the nth derivative of f at a over n factorial times x minus a to the power of n from 0 to infinity. Next slide. There is a question: does fx exactly equals to this summation of terms? For this we want to figure that fn of fi of a over I factorial dot x minus a power to the power of I from 0 to n goes to f of x. So for this also we want to show that absolute value of the nth derivative of f at a over n factorial x minus a power n from 0 to capital N minus f of x goes to 0 when capital N goes to infinity. We want to show this terms by Rn, that is Rn of x is f of x minus the nth derivative of f at a over n factorial times x minus a power n from 0 to n. That is reminder of f of x at a, represented by a. Okay. we can write this one by Tn, that is f of x equals to Rn of x plus Tn of x, that is the summation of these terms from capital N plus 1 to infinity. Tn of x, the fn derivative, the nth derivative of f at a over n factorial x minus a power n, n from n plus 1 to infinity. This is easy to show. This absolute value of these terms goes to 0 when n goes to infinity. We write again f of x is summation c I dot x minus I minus a power n, n from 0 to infinity, that is the nth derivative of f at a over n factorial x minus a power n, n from 0 to infinity. And write Rn, by the Taylor inequality. The absolute value Rn of x less than or equal to e power d over n plus 1 factorial, absolute value of x power n plus 1 when x minus a greater than d. By this the proof is simple. Remember, we can use the ratio test for conversions, to prove convergence of series. If S is a n from 0 to infinity is a series, the ratio test is the famous test for introduce of series to converges. Let define L equals limit of absolute value an plus 1 over an, and when n goes to infinity. We have three cases. Case 1, if L less than 1, then is absolutely convergence. Case 2, if L greater than 1, then S is divergence. And the third one, if L equals to 1, the test cannot be used because the series can converge or diverge. MacLourin series of function fx. The MacLourin series is a special case, a special form, a special method of Taylor's series. If f of x is sigma f n of a over n factorial x minus a power n, and from 0 to infinity, then x minus a less than r less than r. R is sorry, when the absolute value x minus a less than r. So if a equals 0, we have f of x is the nth derivative of f at 0 over n factorial times x to the power of n, and from 0 to infinity. This is MacLourin. This is the MacLourin series of function f. Example 1. Find the MacLaurin series of function f of x equals e to the power of x and its radius of conversion. Are in this inequality are names radius of convergence. F of x is e to the power of x, so the zero derivative of f at 0 is f of 0, e to the power of 0, that is 1. F prime of x is also e to the power of x, so f prime of f at 0 is e to the power of 0, that is 1. We know that fn of the nth derivative of f at x is e to the power of x, so for each n we have f the nth derivative of f at 0 x is e to the power of 0, that is 1. So the MacLaurin series of f is f of x, that is e to the power of x. X is 1 over n factorial x to the power of n, and from 0 to infinity. We can write this by this e to the power of x is equals to 1 x plus x to the power of 0 is 1, 0 factorial is 1, x plus x square over 2 factorial, x cube over 3 factorial, x to the power of by 4 factorial dot dot dot. For radius of convergence we use the ratio test. We have an is x to the power of n over n factorial, so an plus 1 is x to the power n plus 1 over n plus 1 factorial. So an plus 1 over an, absolute value of this ratio, x to the power n plus 1 over n plus 1 factorial by x to the power n over n factorial. We have n factorial times x to the power m plus 1, n plus 1 factorial times x to the power of n. we decomposite this n factorial. Exactly, it's x to the power of n plus 1. We write x times x to the power of n plus 1 factorial. We write n plus 1 times n factorial times x plus n. By cancellation, x power n and n factorial, we have x over n plus 1, that is absolute value of x over n plus 1. Sorry. Okay, we know that when n approach to infinity, the ratio absolute value of x over n plus 1 goes to 0. So L is 0, so the series is convergence, and the ratio of convergence is infinity, because for each x is true. Example 2. Find the MacLaurin series of the function f of x is sine of x and its ratio of convergence. F of x is sine of x, so the zero derivative of f at 0 is f of 0. This means sine of 0, this is 0 exactly. F prime of x is cosine of x, so f prime of f at 0 is cosine of 0, that's 1. The second derivative of f at x is minus negative sine of x, so f prime prime of f at 0 is minus sine of 0, that is 0. The third derivative of f at x is negative cosine of x, so the third derivative of f at 0 is minus 1. So we can write the fourth derivative of f at x is sine of x. This is period, the same as the first, the zeroth derivative. So the fourth derivative of f at 0 is 0. So we find the nth derivative of f at 0 for n equals 4k, that is 0, n equals 4k plus 1, this is 4 in Persian, 1, n equals 4k plus 2, that is 0, n is 4k plus 3, that is negative 1. For MacLaurin series, f of x is sine of x equals the nth derivative of f at 0 over n factorial x to the power of n, and from 0 to infinity, that is 0 plus 1 over 1 factorial x to the power 1 plus 0 minus 1 over 3 factorial x to the power 3 plus 0 plus 1 over 5 factorial x to the power of 5 plus 0 minus 1 over 7 factorial x to the power of 7 dot dot dot. That is, we can notate, use this notation for sine of x equals to x to the power of 2k plus 1 over 2k plus 1 factorial, and from 0 to infinity, because the even terms, all of even terms are 0. Okay, for radius of convergence, an plus 1 over an, absolute value of this, x to the power of 2k plus 1 plus 2 plus 3, 2k plus 3 factorial, that is 2k plus 1 plus 1, x to the power of 2k plus 1 over 2k plus 1 factorial, that is 2k plus 1 factorial times x to the power of 2k plus 3, 2k plus 3 factorial times x, 2k plus 3 factorial is 2k plus 1. That is, we can decompose it by this form, 2k plus 1 factorial times 2k plus 1 times x to the power of 2. The below 2k plus 3, 2k plus 2, 2k plus 1 factorial x to the power of 2k plus 1. By cancellation, we have the absolute value of an plus 1 over an is by cancellation we have x square over 2k plus 3 times 2k plus 2. This goes to 0. That is give us to conclude that the convergence is for all of x. Okay, the next example. Find the MacLaurin series for f of x equals ln of x plus 1. The zero derivative of f at 0 is f of 0, ln of 0 plus 1, ln of 1 is 0. F prime of x is 1 over x plus 1, that is x plus 1 to the power of minus 1, negative 1. F prime of 0 is 1. The next, f prime prime of x is minus 1 to the power times x minus 1, x plus 1 minus 2. F prime prime of f at 0 is minus 1. F the second one, minus 1 minus 2 times x plus 1 to the power of negative 3. So the third derivative of f at 0 is minus 1 to the power of 2 times 2 factorial. We can write this minus 1 to the power of 1 times 1 factorial. The next, the fourth derivative of f at x is minus 1, minus 2, minus 3 times x plus 1 to the power of minus 4. That is, the fourth derivative of f at 0 is 1, 2, 3 minus 1 to the power of 3 times 3 factorial. Okay, we can write the nth derivative of f, at 0 is minus 1 to the power of n plus 1 or n minus 1, no problem. N plus 1, because the power of my negative 1, there is a difference of 1, exactly 1 by the order of derivative, n minus 1 factorial. F of x, ln of x plus 1 is, we want to substitute this one, n minus 1, negative 1 to the power of n plus 1, n minus 1 factorial, minus 1 plus to the power of n plus 1, n minus 1 factorial over n factorial x to the power of n, and from 0 to infinity. We can simplify this, minus 1 to the power of n plus 1 over n x to the n. This is easy to find radius of convergence. A plus a n plus 1 a n, absolute value of this ratio, minus negative 1 to the power n plus 2 x n plus 1 over n plus 1. The next one, minus 1 to the n plus 1 x power of n over n. So find the MacLaurin series of function f of x equals 1 over 1 minus x. In other hand, we want to prove 1 over 1 minus x is equals to x minus x to the power of n, and from 0 to infinity. F of x is 1 minus x to the power of negative 1. So the 0 derivative of f at 0 is 1 to the power of minus 1, that is 1. F prime of x is negative 1 times negative 1. This is derivative of 1 minus x times 1 minus x to the power of negative 2. That is, f prime of f at 0 is minus 1 times 1. The second derivative is minus 1 minus 2 times minus 1 minus 1 minus x to the power of, please introduce, this is 2 minus 1 minus 2, derivative of 1 minus x is minus 1, negative 1 to the power of 3. That is f prime prime of 0 is 2 factorial, that is 1 factorial. We can write the nth derivative of f at x is n factorial. So f of x is 1 over 1 minus x is equals to the nth derivative of f at 0 over n factorial x to the power of n, and from 0 to infinity, that is n factorial over n factorial times x to the power of n, and from 0 to infinity by cancellation n factorial we have n from 0 to infinity. Okay, an is x to the power of n, an plus 1 over an, x to the power of n plus 1, x to the power of n, that is absolute value of x. If it's one, it has to convergence to L, and L less than 1. When n goes to infinity, we have absolute value of n less than 1, so the ratio, the radius of convergence is 1. The next example, you can use this MacLourin series for try your experience in making MacLourin series. The next slide. Some of this MacLaurins was proved. The last one. Thank you. Have a nice day.